Okay, so hello everyone, my name is Nicola Malavasi and I am a postdoc at the Institut d'Astrophysique Spatiale in Orsay, working in the BioPIC team. Today I would like to show you some of the results that I have obtained in the past year, working together with my collaborators to study the relative effect of filaments and nodes of the cosmic web on the spin, star formation and other properties of galaxies. The cosmic web is a complex structure that fills the universe, formed of dark matter, galaxies and gas. It is composed of galaxy clusters at the nodes, connected among them by filaments. The cosmic web is formed by the gravitational collapse of tiny density perturbations in the primordial universe. What happens is that matter departs from underdense regions, which become voids, surrounded by 2D regions which are called walls. Matter flows inside walls to reach filaments, which are one-dimensional structures located at the walls' intersections. Matter and galaxies that are formed in the meanwhile flow inside filaments to reach clusters, which are located at the filaments intersection. Throughout the evolution of all these structure, galaxies are formed and experience their own evolution. They increase their stellar mass, they start as star-forming objects which then quench their star formation, and we know that features of the cosmic web, such as clusters and filaments, and the environment in which galaxies reside may have an impact on their properties. Indeed, there are several indications from the literature that the cluster environment can change the properties of galaxies. In particular, galaxies in clusters are more massive and less star-forming than galaxies in other environments. And they also have a larger fraction, there is also a larger fraction of galaxies with elliptical morphologies. Recently, we have also started to understand that filaments can impact the properties of galaxies. This is an example of my work from 2017, where we detected the cosmic web in the Vipers survey, and we found that massive and passive galaxies are located closer to the axis of the filaments than other galaxies. This is a more recent take on the same topic by Victor Bonjean in 2020, which detected clear gradients of stellar mass and star formation with the distance from the filaments detected in the SDSS. We also know that star formation and mass are not the only properties of galaxies affected by the cosmic web. For example, we know that filament can influence the direction of the angular momentum of galaxies, their spin, which can be aligned or perpendicular with the direction of the filaments. This is an example of the work by Temple et al. 2013, which detected an excess of spiral galaxies with their spin aligned with the direction of the closest filament. And similar results and also other interesting explorations have been carried out by many works in the literature, both from observations and numerical simulations. So our goal is to understand which structures affect the most a given galaxy property. For example, is star formation activity affected more by filaments or by the cluster environment? We also want to understand which property better traces a given structure. Let's say, for example, that we have a galaxy survey and that we have access to all properties of galaxies, such as their stellar mass, star formation, direction of angular momentum. And let's say that we aim at tracing filaments. Which property should we use? Is it better to use the star formation or is it better to use the spin? This stems from works in the literature which have used similar approaches. For example, the red mapper algorithm, which uses the red sequence that is created in a galaxy population in dense environments to improve cluster detection in galaxy surveys, or the work by Rong et al. 2015, which used the average alignment of the spin of galaxies to detect filaments around the coma cluster. So to answer these galaxies, we use the Illustris TNG simulation, the publicly available box. We use the Illustris TNG 300, which is a 300 cubed megaparsec box. which contains about 276,000 subhalos with masses, stellar masses between 10 to the 9 and 10 to the 12 solar masses. We perform our analysis at redshift 0, and the subhalo selection and the filament extraction has been done by this work also from a PhD student in the BioPIC team. To detect the filaments in the illustrious TNG box, we use the discrete persistent structure extractor, or disperse, which is a powerful algorithm which we apply directly on the subhalo distribution. Just to tell you in a couple of words how it works, we start with a measurement of the density field. Disperse then measures the gradient of the density field and detects critical points where the gradient is 0, so maxima, minima, and saddles, and connects these critical points with lines of constant gradient, which we interpret to be filaments. Disperse then applies a persistence cut to eliminate spurious filaments, which are due to the Poisson noise of the galaxy distribution. You can think of this persistence cut as a threshold in the signal-to-noise ratio of filaments. This is an image of the filaments as detected in the illustrious TNG box from the subhalo distribution. We focus on several distances, we focus on several quantities available in the subhalo catalog, such as the stellar mass of the subhalos, the star formation, specific star formation, which is the star formation activity divided by the stellar mass, and the fraction of quenched galaxies, which is computed for the galaxy population with a cut in specific star formation rate. And we also focus on the angle between the filaments and the direction of the spin of the subhalos, which is the angle theta. The spin can be aligned with the direction of the closest filament, perpendicular to it, or have a random orientation. We also focus on several quantities which are derived from the angle theta, such as, for example, the fraction of galaxies with a parallel spin and perpendicular spin with respect to the filaments, which we derive through cuts in the distribution of theta for the galaxy population. And we also focus on this cosine of 4 times theta, which is a quantity which allows us to distinguish two cases. One where the galaxies have either an aligned spin with the filaments or a perpendicular spin, and we combine these two when cos 4 times theta is greater than 0, or the case where the galaxies have a random orientation with the filaments, where cosine of 4 times theta is smaller than 0. And we refer to this case as where galaxies have an ordered relation between their spin and the direction of the filament, and we also calculate the fraction of the galaxies which have such a relation between spin and filaments. We compute 3 distances from the features of the cosmic web for the galaxies, and we explore the variation of these quantities as a function of these distances. Let's say that we are in this configuration where we have a cluster with filaments connected to it. We compute the distance of a galaxy from the cluster isotropically. It's a 3D distance. When galaxy properties are explored as a function of this distance, we can imagine that we are considering the case where galaxies are infalling on a cluster isotropically. We compute the distance of a galaxy from the axis of a filament, and this is the case where galaxies are infalling on the filament, and we compute the distance of the galaxies from the clusters following the path of the filaments. And this distance is computed as the distance from the projected position of the galaxy on the filament to the cluster, and this represents the case of galaxies that have infallen on a filament and then are flowing inside the filament to reach the cluster. In particular, we compute this distance only for galaxies that are outside of filaments, so where the distance from the axis of the filament is greater than 1 megaparsec, and this distance where the galaxies are inside filaments, so where their distance from the axis of the filament is smaller than 1 megaparsec. These are our results, and these are the main plots that I will show throughout this presentation. Here on the x-axis there is the distances to the cosmic web features that I have just introduced. In blue, the distance to the nodes, in red, the distance to the axis of the filaments, and in yellow, the distance to the nodes following the paths of the filaments. On the y-axis is reported the average quantity considered for the galaxies in bins of these distances. On this plot there is the stellar mass of the subhalos, star formation related quantities, and spin related quantities. If we start from the stellar mass of the subhalos, the stellar mass decreases with increasing distance from structures. As you move towards structures, galaxy, regardless of which structure it is and how you approach it, galaxies become more massive. However, there is a difference between the in-filament and the off-filament population, the yellow and the blue curve, where galaxies in filament are more massive than galaxies outside filaments, and there are small differences between the three types of distances, meaning that mass is not a good quantity to distinguish between nodes and filaments, because mass varies more or less in the same way when considered with respect to these three distances. However, if we look at star formation related quantities, we see that star formation related quantities increase with distance to the structure. As you approach structures, your star formation decreases, or the fraction of quenched galaxies increases. And there are differences in the distributions between the three distances that we consider, meaning that the gradient or the amplitude of the distribution allows us to distinguish in which case we are, whether we are infalling on a node, whether we are infalling on a filament, or on a node following a filament. If we look at spin-related quantities, it is very difficult to detect any trend. In fact, these spin-related quantities do not vary much with the distance from the structures. What we can see is that as you approach clusters, in particular, if you approach them following filaments, the spin of galaxies tend to become more perpendicular to the filaments. This is expected because galaxies are formed with their spin parallel to the filament at high redshift, thanks to the tidal torque theory, and then as they flow inside filaments to reach clusters, they merge with other galaxies and their spin becomes perpendicularly oriented. And in our case, this is true also if you approach clusters isotropically. However, the three distributions overlap. It is not possible to tell them apart, which means that spin-related quantities seem to not be particularly suited to distinguish the three structures one from the other. So far, we have focused on a given galaxy property, and we have analyzed how it responds to the three distances that we have considered. However, we can also do the opposite. We can focus on a given structure or a given distance from a structure and try to detect which property is the best one to describe this feature of the cosmic web, to trace this feature of the cosmic web. Which galaxy property varies the most as in response to the distances from this feature, in response to these distances from the cosmic web. So here we have the distance. Here we have nodes, we have filaments, and we have nodes following the filaments. If we focus on the green and the blue lines, which are star formation related properties, we see that they are those that show the steepest gradient and the largest variation from the average in response to the distance to the three quantities, which means that they are the best suited one to trace the various features of the cosmic web. Mass, which is the red line, also shows some degree of variation, meaning that it is also suited to trace features of the cosmic web, in particular filaments. However, spin-related quantities barely show any variation. If we restrict our analysis to low mass, high spin galaxies, so a particularly selected subsample of galaxies, we see that in particular the cosine of 4 times theta now shows, although with large error bars, a variation which is comparable to the one showed by the fraction of quenched galaxies, meaning that in this particular case the cosine of 4 times theta can be used to trace the structures of the cosmic web. This is true also, and I'm not showing it here, but this is true also if instead of considering the full spin of the subhalo, meaning including dark matter, gas and stars, we restrict ourselves also to the gaseous component, which is the spin of the disk, of the galactic disk, instead of the full dark matter halo. As a last point that I would like to make before concluding, galaxy properties do not only show a variation in response to the distance to the structures of the cosmic web, but they also show a variation with the local density, regardless of in which structure they are. This is a plot similar to the one that I've shown you. Here on the x-axis, however, there is the local density as measured from the Delaunay tessellation field estimator, and on the y-axis there are again the average properties in bins of local densities. The three colors are for galaxies outside filaments, inside filaments, or the general population. However, the three curves do not show any difference among the three, so this can be not considered for the moment. So stellar mass increases with increasing local density, star formation decreases, the fraction of quenched galaxy increases with local density, spin-related quantities barely show any variation. And what we wanted to test was whether the trends that we see with the distances to structures were due to the features of the cosmic web instead of being due to the local density, which varies as a function of the distances to the features of the cosmic web. And to do this, we reshuffled galaxy properties with respect to the distances of structures of the cosmic web in bins of local density. This should preserve the relation between galaxy properties and the local density, while cancelling the relation between galaxy properties and the distances to the cosmic web structures. If after this reshuffling we still see a trend between the galaxy properties and the distance to the features of the cosmic web, then we cannot conclude that the trend that we see is due to the properties of the cosmic web, but it could be due to the local density, which changes in response to the distance to the features of the cosmic web. However, if the trend is completely erased thanks to this reshuffling, then we can conclude that what we saw in the original case was due to the features of the cosmic web instead of the local density. This is the same plot as I've shown you at the beginning of this presentation. However, when galaxies when galaxies are reshuffled with respect to their distances from the features of the cosmic web in local density bins. So if we compare this plot with the original one, we can see that in the case of the mass and star formation related quantities, we still detect a trend which is as big as the original one for the reshuffled case. In this case, we cannot conclude that these trends that we see between galaxy properties and distances to the cosmic web elements are due to the properties of the cosmic web. They could simply be due to the local density. However, if we focus on spin-related quantities, we can see that the trends that we saw in the original case are reduced or absent when we reshuffle. This means that although the trends for spin-related quantities with the distances from cosmic web features are much lower than those that we observe in the case, for example, of mass or star formation related properties, these trends could be due to the properties of the cosmic web instead of the local density environment in which galaxies reside. And this could be an indication that these properties are more sensitive to the structures of the cosmic web rather than to local density, and may therefore be better suited to trace the cosmic web. So here I conclude. We found that star formation related quantities show the largest variation with respect to the features of the cosmic web, while spin related quantities show very small trends. However, the spin related quantities are more sensitive to the structures of the cosmic web than to the local density, and this calls for further investigation with larger cosmological simulations or observations to try to quantify how well spin-related quantities can actually be used to trace the cosmic web. Thank you.